Good morning, everybody. Does anybody recognize it? I mean, I know you recognize it. Does it belong to anybody? I think it was left in the 11 a.m. I think it says Davis Murphy on the back, but all right. You have survived the first really hard part of this course. From here until the exam, I mean, teachers shouldn't say stuff like this, but like, it's going to be easier mathematically. It's going to be easier conceptually, and there's going to be like direct application in the form of circuits, electrical circuits, right? So like, I really feel like we are turning like 90 degrees here in terms of like what we're going to expect of you, and you're going to see it today. You're going to see it sort of laid out. And honestly, I think one of the hardest parts about what's coming up is keeping track of all the information that you have to keep track of. But like the math is going to be division and multiplication, basically. Okay, a little bit of solving like 2 or 3 equations with 2 or 3 unknowns. But yeah, nothing like the integrals and things that we've been seeing so far. And why is that? We're going to start applying our newfound knowledge about electric potential to less of these sort of physicsy constructs of disks and rings and lines of charge and stuff like that, and more towards actual physical. I mean, not that those things aren't physical, because what I just described to you were wires and antennas and a bunch of other things. But let's take a sideways turn and see how we can start applying electric potential to real-world situations. And the way we're going to do that is we're going to do sort of a what-if. Let's say I take a conducting chunk of metal, okay, put positive charge on it. I take another conducting piece of metal and put the same amount of charge but opposite sign on it. You now know a lot about what's going to happen here, right? If these two things were not nailed down, what would happen? They'd attract each other, right? Coulomb's law. Could you guess at what the electric field might be doing between these two objects? Yeah, where is it starting? Where's the electric field start? On the positive one, right? And it's going to end on the negative one. So there might be one like that, there might be one like that, might be doing something weird like that, right? But we could come in here, we could draw a bunch of electric field lines, okay. And of course, there'd be electric field lines out here, and there'd be electric field lines coming in like that. So like, we know that there would be a force between them. We know that the electric field exists between them. We could take a stab or a guess at what the lines look like. We could get mathematical formalism in here and integrate some stuff. We're not going to do that. But now you also know that there is going to be a potential difference between these two things. Right? There's going to be some sort of delta V. And why is there going to be delta V? Well, which of these is the high potential? It's the positive one, right? Which one's the low potential? Negative one. Which way is a positive charge going to roll? Downhill, right? It's going to go from high to low, and we could draw the equipotentials in here, right? We know the equipotential's got to look something like that, right? Because it's got to go perpendicular to the electric field lines, right? We know it goes from high to low. There's lots of stuff we know about this situation. But what we don't know is what is the relationship between the voltage, and I'm gonna kind of drop the delta now. I'm getting tired of writing it. Can you hang with me that voltage is always a comparison? Right? It's always like a delta. We're comparing one point with another. It's just the other point we usually compare is infinity. And what's the potential at infinity? 0, right? So I'm just going to start writing V now because we're just going to compare with infinity most of the time. Okay. What do you think the relation, don't write this down yet. What do you think the relationship is between voltage and charge? Like in this situation, we've got two conductors, exactly the same amount of charge, just opposite polarities. What do you think might happen to the potential, the voltage difference, if we say increase the charge? Does the voltage become bigger or smaller with more charge? Take a guess. Bigger? Because bigger charge means bigger mountains and deeper valleys, right? Okay. And if the charge gets less, then those things aren't as tall or as deep, and so the voltage is going to get less. So is voltage and charge, are they directly or inversely related to each other? They're directly related to each other, aren't they? But I've got a fishy symbol in there. The reason I got the fishy symbol is can I just write this? Is voltage charge? No, like unit-wise, one's volts and one's coulombs, right? But even conceptual-wise, charge is something that everything has in the universe, like has mass, it has charge, right? It's a fundamental part of the universe. But potential is a construct, right? It's an abstraction of a force, right? And so they're not the same thing. So how do we fix this? How do we make it so that I can write V equals Q and have it be right? This is a classic physics thing to do. Find a constant that makes it work. I mean, this happened with Newton's law of gravitation. I don't know if you knew that, right? But Newton was like, okay, well, I know that it has something to do with the masses, and I know it has something to do with the distance between them squared, but if you take a mass times a mass and divide by a distance squared, do you get a force? No. You have to put a constant in front of this thing and hope that it is a constant thing, right? If it's not, then you haven't discovered anything. Same thing happened with Coulomb's law, right? Instead of mass, it was charge. You take two charges, divide by the distance, you don't get a force. So what do you need? You need a constant in front. How do I get a voltage and a charge to talk to each other? Invent a constant. And that constant, we'll use capital C as its symbol. We're going to call it the capacitance. Now, capacitance, same root word as the word capacity. So, are we storing something here? Is the fact that I've got two conductors with opposite charge on them, same amount, have I stored something? Huh? Stored potential. Electric potential in this situation. Now, the energy is stored in the field. Okay? The potential is stored in the arrangement of charge. And we'll talk a little bit more about that in a bit. Do note, batteries never store charge. But Mr. Balogh, when my battery in my phone goes down, I plug it in so that it can recharge. Nine, 10. There we go. Okay, I'm calm again. Okay, I had to count to 10 because, I was going to get angry there. Batteries are pumps. They store potential. What does it say on the label? 1.5. That's a clue, right? Okay. It stores potential, the ability to push charge around. Batteries don't store charge. They don't get recharged. If anything, they get re-energized to be able to push some more. But okay, we'll get there. We'll get there. What is this capacitance? It's a thing. It's a constant. We'll hope it's a constant that gives us the relationship between charge and voltage. And I mean, don't do any really hard math here. Can we find it if we know the charge divided by the voltage? Yeah. So what are the units of capacitance? This is a coulomb divided by a volt. Okay, brackets meaning units here. Okay, so coulomb times a volt. We're going to give that a new name. That's going to be called a farad. The units of capacitance are farads after Michael Faraday. 1 farad is 1 coulomb per volt, and it tells you effectively how much a capacitor, or two conductors that are charged oppositely but by the same amount, how much potential they can store in that configuration. Why would I want to store potential? And why don't batteries store charge? Can you think of a situation where we'd want to store some voltage?
You can't generate power.
People always say, Mr. Balogh, why don't we have wireless power? We do. It's called a battery. But you got to recharge it. Okay. Yes, I know what you mean by wireless. You don't want anything in it. You just want to wave it around in the room and have it have power, right? Okay. But there are times batteries are really bad at providing a lot of energy quickly. Batteries are great at providing consistent amounts of energy at lower currents than normal. The thing about batteries is they push for a long time if you're careful, but if you try to get them to push too fast, they blow up. Okay? Capacitors, on the other hand, are devices that can store that energy and that potential and get rid of it really fast. And in a, well, sometimes lethal way. So, where would you need to be able to dump a lot of energy really fast? Right? Clear. Right? And then as part of the medical drama, there's always a problem with the machine. It's either broken, or usually they've used it too much and they have to wait for something. What do they have to wait for it to do? Recharge, right? What's going on there? That's true. You can't use it too many times before it really just needs to build back up enough electric potential energy to be able to do that pulse again. Okay? What's going on there is a capacitor is being filled in the device so that it can then dump. The battery can fill the capacitor, but what it can't do is provide the jolt. So here are various capacitors. You can see they come in different shapes and sizes and flavor. No, not flavors. Don't eat your capacitors, okay? But on the side of them, there'll be some things that tell you, like, don't put it in boiling water and that kind of thing. And they'll usually also tell you, like, what its capacity is in farads. Now, typical capacitors are measured in millifarads and microfarads and nanofarads. Those are very common capacitances. So a farad is actually a really, really big amount. It's a big capacitor. That blue one and that gray one next to it are probably 1 farad or very close to 1 farad capacitors. Anybody that's worked in any kind of car audio has probably run into these big cylindrical capacitors because they're used in car audio to store energy for the subwoofer. But they come in a lot of different, like you can see all different shapes, flat, cylinders, all that kind of stuff. In reality, they are all one geometry, and I'll explain that in a second. But here's just 2 of many examples where capacitors are necessary. I mean, I'm old, right? And I did use cameras that looked like that one, right? And those cameras still kind of exist, right? Professional photographers will still use a nice digital SLR full frame. But that flash that's going off, if you've ever used a camera that's not your cell phone, you know that you can take pictures up to a point. It used to be that the flash in its sequence of re-energizing would emit a tone that the photographer could hear so that you knew it would like start out loud when it wasn't able to work and it would fade. It would actually increase in its frequency, but you would stop being able to hear it. And when you stopped hearing that sound, you knew that the flash would be enabled again. And this would be important for taking different kinds of pictures. We already talked about the defibrillator. Capacitors are everywhere. They are. They're in your power bricks, right? They're a way of sort of quickly being able to put energy in and take energy out of a circuit as needed. Because again, batteries just aren't that good or that fast at doing it. The batteries that we have nowadays. So I told you that capacitors have really just one shape. Even though they might be cylindrical, even though they might be flat, all of them follow the same geometry, and that is a parallel plate capacitor. Essentially what we've got, and this is going to be a terrible drawing, I apologize in advance. I might be able to pull it off. I didn't practice this morning. But there's a plate, and then next to it, how'd I do? The idea is I've got a sheet of conductor, and right close next to it I've got another sheet of conductor. Okay? And then we're going to add like a wire over here, and there'll be a wire coming off that one, and then these wires can go down to something that provides the charge, right? And we'll put plus Q on that plate, we'll put negative Q on that plate, and it turns out that the capacity, the capacitance of this situation can be found from physical properties of the system. It's really quite fun, okay? And what we're gonna use Gauss's law to do it. But before we get there, I know I promised you it would be simple, right? And that we weren't gonna do it, but Gauss's law is the integral you don't see, okay, right? We already know that there's going to be something between the plates. What's the something that's going to be between the plates? Well, there's going to be an electric field there, right? Got charges, they're separated, there's going to be an electric field, therefore there's going to be a potential difference between those things, all that sort of stuff, right? So that means that if I try to employ Gauss's law, right, and I do it, I'm going to wrap my Gaussian surface around only one of the plates. Let me point this out. Hopefully, I don't know if this is obvious or not. What is the net charge on this capacitor? It's 0, right? Okay. The charge on either plate is exactly the same. So if I drew like a Gaussian surface around the whole thing, okay, I'd have a net charge of 0. That means the electric flux would be 0, and I've got 0 equals 0, and I'm not going anywhere, right? So I'm going to be a little bit clever. I'm going to draw a Gaussian surface so it only surrounds one of the plates. I'm not going to draw it on the screen, but I'm just going to think of a surface that encloses just one of the plates. So that means electric field is passing through that surface somewhere, right? And I've got charge enclosed. And we'll just use the positive plate because positive is easier to deal with, right? So I'm going to have an electric field through some area. And if I make the area the same area as my capacitor, it's even easier. I've got my charge on the plate, and I've got epsilon naught, right? So that means that my electric field is going to be Q over the area times my electric field constant, right? And because this plate is parallel, that means the electric field is going to be nice and linear through it. The relationship between the voltage and the electric field is very simple. I could pull out the integral, but it's just a simple linear relationship between them, okay? Well, I can now plug in that this is Q over A times epsilon naught with a D on top. But I'm trying to solve for capacitance, right? Is capacitance sitting in here anywhere? Capacitance is charge divided by voltage, isn't it? I've got a voltage equals a Q over A epsilon naught D. If I divide both sides by V, what's Q over V? It's capacitance, isn't it? And so if I multiply A epsilon naught and divide by D on both sides, then I end up with A epsilon naught over D is equal to my capacitance, right? Or in other words, the way your book writes it, epsilon naught A over D. And notice now, it's true, right? We know that Q equals CV for the capacitor. Okay, charge is equal to capacitance times voltage. But notice in the box at the bottom, all the things in that box are physical parameters of my capacitor system, aren't they? The area there is the area of a plate. How do you find the area of a square? Right? D. That D right there is the separation distance between the plates, right? So there would be some sort of gap between, we can't let them touch. If we let the plates touch, what happens? Positive and negatives combine, wipe each other out, neutral, right? Okay, we want to maintain this separation of charge. So we've got an area, we've got a separation distance, and we've got epsilon naught, which is along for the ride. Again, the constant that is the telltale sign that an electric field is involved somehow, some way. Okay? But now we can find the capacitance of any parallel plate capacitor. Does that area say that it has to be a square? What if we made both of them round? Area is area, right? What if we made them triangles? Area is area, right? What if we made them peanut-shaped blobs? I don't care. As long as the area is the same on both of those plates, I can find how much it can store in terms of separating charge out. It's really, really cool, as long as they're conductors, right? That's the thing. Now, in all practicality, is this a very stable structure? No. And I already told you capacitors are in your phone and your laptops and all your devices. If you open up your phone, will you see just two big parallel plates sitting in there? No. And in that picture I showed you of various capacitors, I mean, there were some flat ones here, right? Kind of down near the bottom. But you notice how most of them are round? What geometry do you think they might be using for the round ones? Cylindrical geometry? Actually, no, it's still parallel plate. Because if you take two parallel plates and then you roll them up, they're still parallel. But now you've got an additional problem. What happens if you take two conductors and you start rolling them? Do you think they might hit each other? Touch, short circuit, cancel out some of the charge, especially as this outer part rolls back in on the inner part. So how do you prevent a conductor from losing its charge or coming into contact with another conductor? Insulate it. Put, I don't know, a sheet of plastic between it. Sandwich plastic, like do like two parallels, and then you put plastic here, you put plastic there, and then you start rolling this thing, you start rolling it up, right? And now you'll never have both plates actually physically touching each other. And as an added bonus, you add stability to the structure, don't you? If you got a nice flat piece of plastic or cardboard or anything else that's an insulator between those two conducting plates, you make the conductors as thin as possible. Let's see, maybe mylar film. And then you roll that whole structure up. It can turn out looking like a cylinder, but in fact, still be a parallel plate.
I know I showed a plate, but did I miss the conversation on what makes it stable and unstable?
Oh, I'm talking about mechanical stability now.
Oh.
Yeah. Because if I just put two plates of mylar out there, they're going to flap in the wind, right? Okay. So yeah, it's a mechanical stability here, like an actual functional. In cell phones, do you want your circuit parts to be big? No. The whole point is to make them smaller, right? This is one way to make them smaller. They can in fact be big, but that if you roll them up very tightly, they can get really, really small. But now we've introduced an insulator into the setup here, right? Do you think that might have an effect on the capacitance? Probably does. Yeah. So what happens now, right? Well, it turns out it's really simple. If there is an insulator, which there always is, okay, then the capacitance is going to be equal to, where did I write it down? Because I wanted to write it down the way you booked it. Another constant times the original capacitance where there wasn't the insulator there. Now, I want you to be very careful. This constant, I'm trying to be very careful as I draw because it is not the letter that you think it is. What letter do you think it is? K. We've already used K, right? K is the electric field constant. So I'm here to tell you that that is not a K. That is the Greek letter kappa. I'm not responsible for this. This is not my fault, okay? What does a kappa look like? Well, where did we get our K from? The Greek letter kappa. Okay? It tends to be more rounded. So our sort of English K, the Latin letters, okay? I keep saying K. Stop saying K. 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 We tend to be very angular with it. Right? Whereas kappa is more. And guess what happens when Mr. Balogh starts writing fast? Just bad. So make sure you understand what the symbol means based on context. If it's F equals squiggly thing Q1, Q2 over R squared, what's that? That's K, right? But if it's capacitance equals squiggly thing epsilon naught A over D, what is it? It's kappa. I'm sorry. This affects every physicist depending on how good their handwriting is. Okay? But notice, is this an increase or a decrease in capacitance? Depends. Is the constant bigger than 1 or less than 1? Right? The answer is for all insulators, kappa is bigger than 1. That constant right there, that kappa, is called the dielectric constant. I think it's spelled that way, okay? Dielectric. Fancy word for something that insulates, okay? So it's called the dielectric constant, and it is different for different materials of like insulator. Not the metallic part of the capacitor, but the insulator part of the capacitor. Okay. All right, so we've got relationships with capacitance, its area. So what happens if we make the area of the plates bigger? What happens to the ability to store charge? Goes up, right? Because capacitance and area directly. What happens as we make the separation distance between the plates bigger? Ooh, it gets smaller. That's kind of interesting. So if we're trying to design a physical structure and we want to maximize capacitance, what do? Make as big plates as possible and get them as close to each other as possible, right? Okay, that will agree. And if we increase our capacitance, like what happens if voltage stays the same, like it's connected to a battery and the battery's maintaining potential, okay? What happens if we increase the capacitance? What happens to the charge? It will go up, meaning that if the capacity is bigger, it can store more charge. How's your brain? It's like, well, duh, right? It's kind of what it says on the screen, Mr. Balogh. We're finally there, right? We're finally, I kind of understand what's going on here, right? Okay? It gets better. Let's do a quiz. Let's do a quiz. Quiz. All right. We talked about dielectrics already. Energy. A capacitor does store energy, and it stores it in the electric field. I'm just going to kind of toss these equations at you because they're not, where they come from doesn't matter that much. But you'll be asked a couple of questions about energy stored in the capacitor. And it's just really nice to just kind of have these in your back pocket for when you're asked about it, okay? 1/2 QV or 1/2 CV squared. 1/2 CV squared is usually the one that's used more often because typically you can't like measure directly how much charge is in your system, but measuring potential, measuring voltage is really easy. What is that unit? What is that unit going to turn out to be? Joules. It's an energy, right? So you're telling me, Mr. Balogh, if I take a farad times a volt squared, I get a joule? Yes, that's what I'm telling you. Don't try to figure it out. I mean, it'll work out eventually, but the rabbit hole of units is starting to get really big. So yeah, don't fall down it. Okay? Now, for a parallel plate capacitor, of which all of them pretty much are, okay? That 11 right there means parallel. Parallel plate capacitor, okay? We know that voltage and electric field be related through that. We know that the capacitance is a function of its physical parameters. No dielectric in this case, okay? So that means that when I plug that in, I would get an energy of 1/2 epsilon naught A times D times electric field squared. And what this means, again, this is for, I'll spell it out this time, parallel plates. The box on the top is generic for any capacitor, any geometry. But specifically for the parallel plate, if we know the energy stored on that capacitor, then we know the strength of the electric field that exists in that capacitor. Of course, needing to know the area and separation between the plates. Sometimes you're asked about energy density. Unfortunately, the symbol for that is a lowercase u. It's literally the energy divided by the volume, okay? And since volume can be written as an area times a separation, right? Between the area and a thickness, it turns out that energy density can be written as 1/2 epsilon naught E squared. So again, just some real quick sort of oh gee whiz results from just knowing the basic equations for capacitors, right? I can tell you energy, I can tell you electric field in something, I can give you the energy density, how many joules per cubic meter is being stored in this system. These are all real practical, like why would you want to know the energy density? What does energy density have to do with anything? Point to the thing that's got energy density that's closest to you right now. Your phone, okay? Your watch. Anything with a battery in it has energy. And what's the problem with electric cars? Why aren't people just buying electric cars as fast as they possibly can? Batteries are expensive, and they're heavy, and the energy density of a commercial grade battery isn't nearly as high as gasoline. You put a gallon of gas in your car, you can go places, right? A full gas tank in a typical size car can take you almost 400 miles, depending on the kind of driving you're doing. Electric cars with really big batteries can push maybe 300 miles, 350 depending on the design, right? And then it takes a long time to get that battery back up, whereas filling a gas tank and, you know, just, right? So there's that friction that's sort of built, and it comes down really to energy density. Toyota. Used to love Toyotas. I hate Toyotas now. Toyota has been jumping on the hydrogen bandwagon. Like, when was the last time you saw a hydrogen-powered car? Where are all the hydrogen-powered fueling stations? There's one at the airport in San Francisco. Good luck if you're here in Fresno and you run out of hydrogen, right? Okay. Hydrogen's got a lot of problems. But the reason hydrogen, now hydrogen's really cool because you burn hydrogen and what do you get? Water, right? I would love water vapor to be the thing that comes out of everybody's tailpipe. I would. I think that would be incredible, right? The problem with hydrogen is its energy density. You can build as many refueling stations as you want everywhere. You're still going to have to stop like every 100 miles to refuel because you simply can't store that much hydrogen on the vehicle and get the same energy density as you would for gasoline is terrible. Gasoline is awful. Gasoline poisons us. It changes our atmosphere. Don't drink it. Don't smoke it. Okay? But what it has is energy density. It really does store a lot of energy in a very small volume. And our society, our culture, the way we move food, the way we do stuff depends on energy. It depends on energy flow and getting the most amount of energy in a spot to do useful work.
So what, is it just like materials for batteries?
Yes. It's research, it's materials, it's the fact. Have you heard in the news, like every once in a while, there's this brand new battery and it's going to change how batteries do? In the lab, we have batteries that can, it's just like, okay, they can charge fast, they can discharge fast, they're really good, right? Making those at scale is turning out to be really hard. It's just getting enough batteries to satisfy the demand that can do quick things, right? I mean, come on. If we made an electric car that could refuel in 5 minutes, would people have range anxiety anymore? No, because it would be like refilling, right, your gas tank, okay? Problem solved. The problem with making a battery like that is economical and safe, that's the bigger problem. That's your charge, you electrical engineers and chemists. Make a battery that works. They work. Lead acids work, but they're really heavy, and they take a long time to charge. All right, so that's why we're talking about these things. Okay, I forgot to tell you, I'm doing all of this chapter today. We're pretty much done. I've got one more thing to teach you. It's going to take the rest of our time because it's a little bit complicated, but it's not that complicated. But like, I'm doing one chapter today, and I'm doing one chapter on Monday. What chapter are we in now? 25? Okay, and then we're going to do 26 on Monday, and we're going to get started on 27, which is going to take us 3 days. Because really, authors of books, this chapter and the next chapter should really be one chapter. Not sure why they're separated where they are. Chapter 27 sort of brings together everything that we'll learn in 24, 25, and 26, right? And apply it all to electrical circuits. But what we're going to do now is I'm going to teach you some of the basics of thinking about electrical circuits, but really the only thing we know about so far are batteries and capacitors. On Monday, we're going to talk more about batteries in particular. For right now, it's enough to know that a battery provides voltage. That's it, okay? We'll talk about why and how and chemistries and things on Monday. But we need to talk about how things are connected together and then apply that to the specific case of capacitors in electrical circuits. So there's two ways that electrical things can be connected: series and parallel. What does it mean to connect something in series? Like if I have 3 capacitors, how would I connect them in series? King? Directly from one to the other, right? So like, and this is where I'm going to start drawing very poorly. The symbol for a capacitor in something called a schematic circuit diagram is 2 parallel plates with 2 wires coming off of it, right? So this would be like capacitor number 1, okay? And then if I wanted to connect capacitor number 2 in series with capacitor number 1, how would I do it? Well, I just connect them as if they were like train cars, one after the other, right? So if I want to add a 3rd capacitor in series to this, how would I connect it? Uh-oh. Capacitor's oriented differently. How do I connect it in series? Ooh. Usually that's drawn with a nice corner to it. And then if I had one down here, how would I connect it in series? Connect a wire between them, right? Now, the thing is that we need to be really clear about, okay, is that series and parallel are always referenced between 2 points, and those points are usually a battery. Do you notice how my symbol down there at the bottom of that circuit diagram has 2 parallel plates in it, but one of them is shorter? That's a battery symbol. For a DC battery, for something that puts out direct current, which is most of what we're going to do in here, okay, this is a battery. It has voltage, okay? Now, fair warning, Mr. Balogh is drawing circuit diagrams very quickly. Is there a tendency for his capacitors to start looking like batteries? Yes, right, okay. So usually I label them to remind myself, right, which one is which. So yeah, just watch out. The other symbol that's used still fairly often, I see this one used quite a bit still, and I wish it would die. Sometimes a battery is drawn like this. And there'll be different numbers of small and large plates in them. I was going to go into this on Monday, but let's just cross this bridge right now. The word battery has an old-timey meaning, like an ancient, like it was never applied to electrical. Before electricity existed, the word battery existed, and it referred to like a collection of things. So you might have an artillery battery or a battery of artillery. You might have a battery that is an ammunition storage. It's usually applied to like wartime things, right? Okay. But the battery of guns, the battery of cannons, it was like a collection or a group of things. They use that word battery to describe it. So when Alessandro Volta was developing this chemical system that had just like a plate of copper and then some lemon juice and a plate of zinc and some lemon juice and a plate of copper and another piece of fabric with lemon juice in it, right? And he had basically what was a bunch of repeating similar structures. What did he call it? He called it a voltaic battery. Kind of egotistical to call it after himself. But yeah, right, okay. And then that was shortened to just a battery, right? So nowadays we don't use the term battery to describe group of things. We just use it to describe that thing that stores electric potential, okay? But that's why some of these symbols show multiple copies of the same thing, right? You can add more voltage, but whatever. I point that out because every once in a while it sneaks in, like in exam problems and things like that, where if I pull it out of a different textbook or I pull the picture out of a test bank, they'll do something like that. Okay, but notice that it's in series with the battery. And as in a battery, in this symbol, the long side, oh dear, the long side is the positive side and the short side is the negative side. Charge would flow or get pushed by this battery from the positive plate through the circuit, running around clockwise. And as I go around clockwise, I have to go through each capacitor in turn. The way that you know things are connected in series is that there are no junctions between the two things. If you're looking at two things, are these things in series? Look for a junction. If there's a wire that directly connects and doesn't go through a junction, you know that you're in series. Now that I've talked about junction, let's talk about parallel. This is series, okay? And we'll do parallel over here. How would I connect capacitors in parallel? Well, you kind of draw them the way it says, right? So if I got a capacitor there and a capacitor there and a capacitor there, right? Then coming out of the battery, I could come up and hook capacitor number 1 into the battery. Now, capacitor number 1, is it in series right now? Sure is. There's no junctions anywhere, okay? But if I now make a junction, I come up here and go through capacitor 2, and then again through capacitor 3, how many junctions are in this circuit now? 4. Where are they? 1, 2, 3, 4. Every place. What? Oh, it just didn't show up because I used a bad color. We'll use purple. Is the purple showing up better? No? I made them a little bit bigger. So those are the 4 junctions right there, right? Okay. A junction is where 3 or more wires come together in some way, shape, or form, right? Is this thing up here a junction? No, that's just a bend in a wire, right? Don't get fooled by them. Okay? This is not a junction. It's just a bend in a wire. Schematic diagrams tend to be drawn on like grids. Okay? So it can be very clear what's going on. These 4 are all junctions, and it's those junctions that are the dead giveaway that something is connected in parallel. All right. So that's like a visualization for how to connect things together. And again, right now, since all we know about are capacitors, we're only going to be dealing. Eventually, we're going to have resistors that we'll put into our circuit diagrams, and batteries, and all kinds of stuff is going to start happening. All right. Let me move this out of the way because I needed this space for something else. So I'll just put that up there. All right. When it comes to series and parallel, there's things that we can say about the charge and voltage that is in these systems. Okay? What do I mean by that? Let's take a look at the series case. We connect the battery. The capacitors initially have no charge on them, meaning they're neutral, but they always stay neutral. What we mean by a charge on a capacitor is that we've pushed stuff onto the plates, right? So as this battery gets hooked up and it starts pushing positive charge to the left and negative charge to the right, that positive charge is going to migrate around and it's going to pile up on the plate, the first plate of the capacitor gets to, and then there's just empty space, right? Can that charge flow anymore? No, it's physically prevented because it's just empty space or maybe a dielectric there, right? Can't get through. What's the negative charge going to do? It's going to pile up on the other side, isn't it? Right? And notice now how it can't get any further. Two lovers separated by vast distance, right? They so much want to be together, but they are not allowed to, right? Okay? But take a look at, like, I don't know, this structure right here. What is this? The plates, it's an H. The plates of the capacitors are what? Conductors or insulators? Conductors. The wires are what? Conductors. This is a big conductor. And if you stick a conductor, which is neutral, next to a positively charged thing, what's going to happen to all the negative charges in that conductor? They're going to try and get as close to positive as they possibly can, right? So that means negative charge will get polarized or pulled, right, over to that plate. Positive charges in that conductor will get pushed away, and it's all equal, right? If 2 charges are there, then 2 negative charges come over, 2 positive charges. But now what happens in the next segment? We're applying all this stuff that we learned in the first unit. That's not fair, Mr. Balogh. I wanted to forget that. Coulomb's law is still here, right? And it ends up polarizing with exactly the same amount of charge. And so what can you tell me about all of those capacitors? What is the same? What is identical? The amount of charge that's on them. So for capacitors in series, the charge is what I call the same. Okay? Q1 is equal to Q2 is equal to Q3 is equal to ... What am I trying to say here? If I've got 4 capacitors in series, I know the charge on them is all going to be the same. All right. The thing that's different, the thing that has to be true, this battery has a certain amount of electric potential or voltage in it. Let's say, I don't know, 3 volts. Okay? That voltage, that energy is going to get split up and shared between the capacitors. The charge is the same, but the voltages will be different. If Q is the same for every capacitor, but every capacitor is different, what must be true about the voltage on them? It has to be different as well. But by conservation of energy, the sum of all the voltages on the capacitors in this circuit has to be what you started with. If you start with 3 volts, then everything has to add up to 3 volts. If all 3 of those capacitors were the same capacitance, what would each one get? 1. And because 1 plus 1 plus 1 equals 3. So the way that we say that is that the voltage is shared. And so that means the total voltage, the voltage coming out of the battery, is the sum of the voltages of the capacitors. These are just the mathematical statements that say charge is the same on all capacitors or equal on all capacitors when connected in series, and voltage is shared. You have to split it up. You can't go over the total. Okay, so what does that mean, Mr. Balogh? Well, if we rearrange our master equation here, the master equation is the relationship between charge, capacitance, and voltage. To solve for a capacitance, and I come down here and I go, okay, well, I know Q is the same everywhere, right? Q over V, like Q total over V total. Well, this is going to be Q1 equals Q2 equals Q3 equals dot, 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 divided by V1 plus V2 plus V3, dot, dot, dot. I probably should have written this as a Q total, not the, I mean, it's all the same, right? But we can add all those up to get a total charge, okay? Notice, what's Q1 over V1? It's C1, right? Okay, this is C1. What's Q2 over V2? C2, okay? I did this all wrong. Did it wrong. I'm glad there's an undo button. I was reading the parallel side of my notes instead of the series side of my notes. Sorry. I was right putting equal sign in them. Read your notes correctly, Mr. Balogh. There we go. Okay. Being able to split this up is not as easy. I can't just add things together when I got equal signs on the top like that. What I can do is invert this. In other words, 1 over C, and this would be like a C total, would be equal to V1 plus V2 plus V3 all over Q1 equals Q2 equals Q3, just dot, dot, dots, okay? Now my denominator is the same, now I'm good. But what is V1 over Q1? It would be C1, wouldn't it? 1 over C1, okay? So 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. I'm sorry, I should have done this one second. Let's ignore that for just a second. Let's go over to parallel. That was my bad. I read my notes wrong. You want to take a guess as to what is exactly the same in parallel? This time it's the voltage. Why? How do we know the voltage is the same when things are connected in parallel? Take a look at this. These positive charges coming out of this battery. Let's say the battery sends out 3 positive charges, right? Okay. Where are they going to go? Onto all 3 at the same time, right? Now, the amount of charge is going to depend on their capacitance, but they'll all pile up there, right? And same thing, negative charges will flow out the other side and they'll pile up on the other side, okay? But the battery can kind of keep pumping charge, right? Until the voltage on the sum of the voltages equals the same as the voltage of the battery. So if the battery's voltage is 3, it needs to wait until we get 3 volts on all the capacitors for everything to even out and for the battery to stop pushing. So voltage for a parallel plate capacitor is the same. In other words, the voltage coming out of the battery is equal to the voltage on 1 is equal to the voltage on 2 is equal to the voltage on 3 is equal to da. You want to guess what the charge is?
Wait, you just said the total voltage is also equal to the individual voltage?
Yes. Yes. If the battery is 1.5 volts, then all of them will be 1.5 volts.
Gotcha.
It's the same. Because the battery can just push out until it's done. It doesn't have, it's not forced to split up between the capacitors.
So it's, you said 1.5?
Sure.
Each?
Yeah. Yeah, if the battery's 10, then they all have 10. In parallel, the voltage is the same. But the charges are all shared. Okay? In other words, if one of these has a bigger capacitance, right? Let's say it can store 3 charges, right? And the others can one can store 2 and only one can store 1. Then this thing the battery puts out 6. And the charges get split up based on the capacitances. Okay? In series, all the charge was the same, and it was the voltage that got split up. In parallel, it flips. Voltage is the same, which means that the charge has to be different if the capacitances are different. So we say that this is shared. Okay? And now I can write my C total, and now it's going to be right. Q1 plus Q2 plus Q3 all over V1 equals V2 equals V3 equals ... And as you said before, this is C1 plus C2 plus C3. Notice, down here at the bottom, took a while for us to get there, and I kind of did it backwards, I'm sorry. When we add capacitors in parallel, we add their capacitances together. We end up with more storage ability when they're connected in parallel with each other. And we write down that C total down there is also called the equivalent capacitance. I'll often write C subscript EQ for equivalent, meaning that I could have 3 capacitors or, okay, so let's say I had a capacitor that was 1 farad, 2 farads, and 3 farads. What would be the equivalent capacitor if I wanted to replace it with just a single capacitor? What's 3 plus 2 plus 1? 6. I could replace all 3 of those with a 6 farad capacitor and have exactly the same electrical storage. Okay? But what happens with capacitors in series? Do they just add their capacitances together? They add their inverses. What does that mean? Well, like 1 over 1 plus 1 over 2 plus 1 over 3 is a number that is much smaller than any one of the individual capacitors in there. So adding capacitors in series has the effect of reducing the amount of charge and voltage that can be stored in a capacitor system, which sometimes is what you want to do. Sometimes you need to have a capacitor for a reason, but you also don't want to store a lot of energy in that structure. So putting them together in series can really, really help with that. Now, where this is going and what you will be asked to do, okay, is I'll start this example and we're going to finish it on, I've got 5 minutes left. I'll finish it on Monday, okay, and then we'll move into resistors because we're going to do the same thing with resistors, okay, we need you to be able to look at a circuit and the circuit diagram and be able to not only tell us things that are wired in series and parallel, but be able to work through a circuit diagram. So what do I mean by that? I'm just going to label these things here. So I've got a battery. How do you know it's a battery? Symbol, and I put a V next to it, right? Okay, so it's a battery, right? And then I've got 4 capacitors. I've labeled 1, 2, 3, 4. Okay. Is there anything here that jumps out at you that you could tell me for sure the connections between capacitors? It's okay. So the question is, you're looking at this diagram. I want you to tell me what's in series and what's in parallel. Is there something that you are 100% sure is in parallel?
Yes.
Which ones? 2 and 3. Why are they in parallel? There's junctions, right? You look and you go, ah, junction there, right? Okay, now, is C1 in series with C3? No. Why not? There's a junction there.
Is it in series with 2 and 3?
Yes. It's in series simultaneously with 2 and 3. Whoa, 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 whoa. Circuit analysis is the art of looking at these pictures and being able to determine series and parallel connection. And the way that we're going to survive it is by doing something called circuit reduction. We are going to attempt to reduce this circuit's complexity down to the simplest possible circuit we can get. What would be the simplest possible circuit that consists of a battery and a capacitor? It would be a battery connected to a capacitor, right? That's the simplest thing we could ever have, right? So the question is, how do I get from this thing to this thing? The answer is series and parallel rules. We just figured out that you can put capacitors together in series and parallel and have different things happen, right? If they're in parallel, we add capacitances together. And if they're in series, we invert those things, right? So I can take a look at this thing. Let's take a look at this combination right here. We know that those are in parallel. How do we know they're in parallel?
Junction.
The junction. In other words, charge would come in, would force to get split, would pile up, and then come back together here. That's a parallel branch. So I want to redraw this picture to represent that. Okay? So I still have my battery. I still have C1. But now I'm just going to draw a new capacitor connected to C4 and back. I've eliminated the parallel part of my diagram, but what is that new capacitor going to be? Yeah, we'll label it C23. Okay, but what is C23? Well, it was a parallel connection, right? And what do the parallel rules say for what I do with the capacitance? I add them together. Now, on Monday, we're going to put numbers to these things, right? I'm stepping you through it once, and then we're going to kind of do it again so we get some more familiarity with it, right? But we would add those two together. And now looking at this diagram, the new diagram, can you tell me what the connections are between C1, C23, and C4? They're all in series. And why are they all in series?
No junction.
There's no junction here, right? So this is a series connection. This was a parallel connection, right? And how do I add things together in series? You add their inverses. I would end up with a picture that looks like this, where my C total or my C equivalent would be 1 over C1 plus 1 over C23 plus 1 over C4. And now I know the total capacitance of this circuit. Even though the real physical circuit was laid out like this, theoretically, mathematically, the total capacitance will be that. And then we will continue this on Monday, where we are going to apply this rule, the relationship between charge, potential, and voltage, to find out what the charge and voltage is on every single capacitor in that circuit. That's where we're going, and we'll pick up that thread on Monday. How was it today? A little bit better, right? Faster. I'm moving faster. But like math, was the math hard? No. Concepts, I mean, it's not nearly as bad as Gauss's law, right? Have a great rest of the day. Come to grasp.